Now that you know how to calculate the centroid, and in turn where the neutral axis is on a section, we're going to move into calculating the moment of inertia. We need to know the moment of inertia because that can help us predict things like how a shape will be impacted by bending or stress. So if you I'm going to have you re-download the text from the last unit, last exercise, because I've added some things to it. So you'll need to re-download that, and then there will be an Excel file on Unit 4.2 Moment of Inertia. So I'm going to switch over to that Excel file and a bit of a little sketch pad here. So the first example 2 in the text is just finding the moment of inertia of just a rectangular wooden beam. And this is a pretty easy process for such a simple shape. So the text gives us a wooden rectangular beam that has a size of 6 by 12 or a nominal size of 11.5 by 5, or 11.5 by 5.5. So determining the neutral axis of a beam like this is real easy because it's just going to be your x-axis on this is just going to be half of 11.5. Actually, we don't even need to know that for this. We just need to, we don't even need to know that. So forget that. Don't even look at that. To calculate the moment of inertia for a shape like this, we have to take this formula here, which I is what we use for moment of inertia, equals our base, so that's 5.5, times our depth or height, which is 11.5, cubed over 12. And that will be a constant for when you have the neutral axis about the center of the section. If you're calculating it from the axis in a different spot, then you'll have to use a different equation, which we'll get into in the next example. So that's as simple as just coming over here, pressing equals. So that's your base times depth or height raised to the third divided by 12. And that's that. There are tables out there where they have a list of different rectangles, rectangular beams, and the moment of inertia on those. I think using Excel kind of almost makes those tables kind of obsolete because we can easily make our own calculators instead of having to thumb through a table, but that'll be a different assignment down the road. So moving on to example 3, we have a angle, and this gets a little trickier. So with the angle, we're going to need to calculate, let me do a quick sketch of that. So my angle was going to be 8 by 6 with a thickness of 1. So in the example that I'll have uploaded on the Excel, we have our base of 6, our depth or height of 8, and t, the thickness of 1, which that's kind of hard to see there. So we're going to need to calculate where the neutral axis is on this shape. And so as we did in the last exercise, we're going to split this into different shapes. So we have a rectangle here and a rectangle there. So I've already gone through and calculated that. I have a base of 1, height of 8, calculate my area, and then calculate that centroid about the x. Then do the same thing for this shape. It has a base of 5 because we got a thickness of 1, so 5 by 1, do all that calculation, sum up the moments, which is your area times the centroid, and then the sum of the areas, and then it's just the sum of the moments divided by the sum of the area, like we just did in the last section. So knowing that, we know that our x-axis here is about 2.65 from this bottom edge. And when we're going to once again split our shapes into simpler shapes. So we have, let me do a little different color here. Sure, this would be fine. So we got a rectangle here. And we'll treat this whole area as 1. And then I'll do a red color here. This will be a negative area rectangle. So we're going to need to do the moment of inertia for each of these 3 different shapes. So we'll use this first shape here, and measuring from the x-axis here. Since the axis is at the bottom edge of the shape, we're going to need to use the equation or formula. Sure, I'll drag another color in here. I equals base times depth raised to the 3rd, oh, that's ugly, over 3. So in the last one, we had the axis in the center, so we used base times depth to the 3rd over 12. Now the axis is at the bottom of the shape, or in this case, these 2 shapes on the top, we'll use base times depth raised to the 3rd divided by 3. So let's fill that out. So my base is just 1, and actually I had these all kind of named, so it's equal to t. And then our depth is 8 minus our location of our neutral axis in the x. So that's 5.35, and then our moment of inertia for that is going to be base times depth raised to the 3rd divided by 3. And then we'll do the same for this one, so that our base on this one is going to be 6 times, in this case I'm going to do 8 minus our location of the neutral plane raised to the 3rd divided by 3. I put that in the wrong spot. Well, that's fine. I'm just going to drag this down here. I should have, if I was going to do what I had set up here, I'd put B as whatever. That's fine. And then last one here is going to be our -1. So that's going to be equal to 6 minus the thickness. And then the location of the x-axis minus our thickness. And then I'm going to copy this one here because it's the same equation, paste it down there. And that is not the same equation. Let's swap things out here. It's one issue of naming cells is that it won't allow you to copy things as easy. And then to solve for the entire moment of inertia of this angle, we're going to take the sum of all these, but knowing that the last one there is a negative. So control, and I'll put a negative in front of this. Now this number, actually, now that I'm looking at it again, this is way too big. Let me just do this the way I should have done in the first place. Close that. And then I'm going to put okay, that's a better number. Calculate the moment of inertia among many other things. So opening up that, I clicked on my let me do that one more time. Section properties. And I'm going to come up here to flanged and click for this, in this instance, a L shape. And then I'll set my thicknesses. This dimension here, be careful, that is from the top of it to the top of this leg, not the overall height. So I'm going to put 7, and then our width of 6. And then just click compute. And you can see right here, we got 80.77, or rounding up 80.78. So as you go work through the problems, you can use MD solids to make sure that you got the correct answer. Let's close all this down. And then another thing we can, a thing I found is on a website, which is in the text, Engineering Toolbox. And I'm going to do a quick search of, let's see if I can just find it in here. Now there's a lot of stuff in here, so I'm just going to type moment of inertia. I need area of moment of inertia, and I have links in the text for all this stuff. And if I come down to, so I got a bunch of different shapes with the calculation formulas to calculate the moment of inertia for each of them. And let's see here, cross sections 2, it has this L shape, and let me kind of see if I can get this to, where's my cursor at? I have an example 3 simple. So using the formula as I have on here, we can reduce the amount of math we do by a great deal, and at the same time even calculate the moment of inertia about the y-axis as well. So I have all my givens here. I have B1, which that is the distance from this edge to the inside of that leg, and H1, which is from this edge to the top of this leg. And then our XD, which it layouts it here, is from this edge to our y-axis, our neutral plane, neutral y plane, and neutral x plane, which they don't actually have labeled very well in here. Like YD, they don't have that in here, but that would be from this edge up to this axis or plane. So the equation for that, let's just quick delete these and redo them, is going to be equal to our base squared plus H1 times thickness divided by 2 times our base plus H1. And then I'm going to just copy this again because the YD is very similar, just swapping out a couple of the numbers there. So it's going to be our height, base 1, height, base 1. And then there's a big old equation up here to calculate the moment of inertia. I'm not going to bore you with typing that all out because you should be able to read this. So just typing that in, that will give you your moment of inertia for X and Y. So as you work through your problems, you can go look at this site and see if there's anything useful, or go through the longer process of breaking the shape down into simple parts and then doing your calculations from there. So on the problem sheet here, if I can find it, here we go. I've given you a section, as always, for given, and then a lot of area for solving. All I need is the moment of inertia about the x-axis, but I want you to show your work. That'll be part of the rubric I have set up, that I need to see work. I don't want to just see that you type this number in here. I want to see that you did some math up here, label it, and then down here I have a box next to it that also will show that formula. So show your work, and then use MD solids or this site to find a formula that makes it a little easier, to get the right answer. You should have free control over this, so you can like right click on this row, insert, and add more room if you need it. And then when you're done, go ahead and load it up to Canvas.